Draw angles in standard position. Well, we're going to go through just some definitions here. Where do we start? We'll start with what? We'll start with?
A ray consists of one point on a line and all points extending in one direction from that point.
Okay, then what?
An angle is the union of two rays having a common endpoint.
Very good. What's that endpoint called?
The endpoint,
the endpoint is called the vertex of the angle, and the two rays are the sides of the angle.
All right. Keep reading.
We leave one side fixed in place and rotate the other. The fixed ray is the initial side, and the rotated ray is the terminal side.
All right, so we kind of start at the initial side. We begin the rotation, and we end at what? We end at the
terminal side.
Terminal side, and we get ourselves an angle. Does that look like an angle?
Does to me.
Mm-hmm.
And that angle's in standard position. When is that angle in standard position here? Help me out. It's in standard position when?
If its vertex is located at the origin and its initial side extends along the positive x-axis.
All right. So here's the x-axis, and here's the y-axis. So next thing we're going to do is see if we can talk about degree measurement. And to talk about degree measurement, I'm going to start by saying the measure of an angle is just the amount of rotation from the initial side. So if I take a look at a circle, 1/360th of that rotation is a single degree. It's kind of arbitrary. But that means if I start at the positive x-axis, I have 0 degrees. If I rotate all the way around, I'm at 360 degrees. So halfway would be 180 degrees. 90 degrees would be a quarter of the way. And then if I go ahead and take a look at 3/4 of the way, that would be 90 and 90 and 90, that would be 270 degrees. Now, notice, if you will, that when I rotate, at least from the way I drew this, what happened? When I rotated upward from the positive x-axis, this was considered a positive rotation. So if I was to rotate downward from the x-axis, this would be considered a negative rotation. So when I sketch my angle in standard position, the vertex is at the origin. And if I'm sketching an angle in terms of 60 degrees, I kind of keep in mind that I have 0 degrees, 90 degrees, 180 degrees, 270 degrees as a guide. The very last thing I'll say before we begin, so you and I can communicate, as I begin to rotate upward, as I pass through each quadrant, numerically, I'll just number them. I would go from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4, and this would follow the rotation of a positive rotation going upward from the x-axis. What quadrant would 60 degrees be in?
Would that fall in the first quadrant?
And that's very good. And so if I rotate upward, I would go ahead and say it'd be about 2/3 of the way, right, and I would have 60 degrees. What quadrant would 190 degrees fall in?
Would that be in the third quadrant?
Very good, because if I rotate halfway around a circle, I've rotated how many degrees?
180.
How many more do I then need to rotate? Another?
10 more.
10 more. So that rotation would be 190 degrees. Now when I take a look at the third angle, negative 225 degrees, I'm rotating upward or downward from the positive x-axis?
I think you're going to go downwards.
Downward. So as I start to rotate, as I rotate all the way down to the negative part of the x-axis, I've got negative 180 degrees. Right. How much further do I have to go?
Another negative 45 degrees.
Nicely said. Very nicely said. And 45 is half of 90, so that's about halfway through the actual quadrant. So there's negative 225 degrees. For 750 degrees, this is a bit of a drag because I have to rotate in a positive direction once around, twice around. Well, if once around is 360 degrees, twice around would be what? It would be?
720.
How much further do I have to rotate? Another?
30 degrees.
It's about 1/3 of the way. So there's my rotation of 750 degrees. Now, the other unit of measurement is called a radian. And 1 radian is the angle that's formed when you go ahead and take a look at the arc that's subtended. It's what it's called. It's intercepted. Its length is identical to the length of the radius. that rotation always occurs in the same spot. And that is the definition of 1 radian. So if I continue to rotate to find where 2 radians would be, and eventually to continue to rotate for 3 radians would be, by the time I get halfway around my circle, I'm at 3.14159 radians, and that's pi. So a complete rotation, well, that would be 2 pi. And now just in terms of dividing up my rotations, if I have a rotation of pi out to the negative part of the x-axis, I guess I would have half a pi up to the positive part of the y-axis. And lastly, and here's a big old sentence, if I go ahead and rotate to the negative part of the y-axis, I'm just counting 0, pi over 2, pi, and then another pi over 2. So now you have 3 pi over 2. So I can use this information to sketch in standard position. Pi over 3, a third is less than a half. What am I driving at? What quadrant would this rotation be in?
I think it would be in the first quadrant.
First one, very good. So we would sketch pi over 3. 8 pi over 7, I got to think in terms of fractions. 1 pi is 7 over 7 pi.
Okay.
Why do I mention that? 8 pi over 7 would be a little bit more than that. Therefore, this rotation would fall in the
third quadrant.
third quadrant. Very good. Negative 3 pi over 4, the rotation is not upward, it is
Downward.
And again, I got to think in terms of fractions, downward. So negative pi over 2, in terms of a denominator of 4, could be negative 2 pi over 4.
Right.
Negative pi would be negative 4 pi over 4. Am I just rambling, or is there a reason why I mention this? What quadrant is this rotation in?
In the third quadrant.
Third quadrant. Very good. There's my rotation of negative 3 pi over 4. Right over here. And for my very last case, I'm looking at a rotation of 19 pi over 6. Gosh, I got to think about this. If I rotate 2 pi, that's 12 pi over 6, isn't it?
Yes.
That's once around. How much further would I have to go to get 19 pi over 6?
7 pi over 6?
7 pi over 6. So if I rotate another pi, that's 6 pi over 6. I'm almost there. I go a little further, and now I'm at what? I'm at?
You are at 19 pi over 6.
Very good. Thank you. Sketch each angle in standard position. So I'm going to go ahead and sketch my axes. I have an x-axis and a y-axis. And for part A, I'll sketch an angle of 30 degrees. Positive 30 degrees means we're rotating upward from the positive x-axis. Now, a rotation out to the positive y-axis is a rotation of 90 degrees. So I would like to rotate a third of the way through that first quadrant. And so if I rotate a third of the way, I'll have my rotation of 30 degrees. For negative 135 degrees, a negative rotation is a rotation downward. If I rotate to the negative y-axis, that would be negative 90 degrees. If I rotate to the negative x-axis, well, that's a rotation of negative 180 degrees. Negative 135 degrees would be halfway between that negative 90 degrees and the negative 180 degrees. So there I have my rotation of negative 135 degrees. Convert angle measures between degrees and radians. A couple of quick reminders. We know that a degree, it's kind of an arbitrary unit. It's 1/360th of a circle. While a radian, well, 1 radian is going to be that specific angle so that that subtended or intercepted arc and the radius are equal. And we know that if we rotate all the way around a circle, we could represent it as 360 degrees or 2 pi, and that rotation would look something like this. If we rotate halfway around a circle, well, that means we can refer to that as 180 degrees or pi. So we can use either of these relationships to just set up a proportion. And the proportion just says degrees is to 180 as the radians is to pi. Why does that matter? Because if I give you a degree measure, you can now find the radian measure. If I give you a radian measure, you can find the degree measure. So we'll start by giving you degree measures, 3 of them, and switching over to radian measures. And all we're going to do is use a very simple thought process, which is that we're going to go ahead and say if we're given 60 degrees, we know 60 degrees is to 180 degrees as what we're looking for, and that's the radian measure. X is to the equivalent of 180 degrees, which would be
Pi.
pi in radians. And we'll just solve for x. And solving for x is pretty quick. We'll multiply both sides of the equation by
Pi?
pi. And the degree unit will cancel. So now we have 60 pi over 180 is equal to x. And 60 over 180, that's 1 over 3.
Right.
So now we have 1 pi over 3, or pi over 3. Fractions become very important in this part of the material. For the second rotation, nothing is going to change. It's a rotation over 210 degrees. What will change is how we do it. What would the setup look like? You'll tell me this time.
I think it would be 210 degrees is to 180 degrees, as our radians x is to pi.
Beautifully said. Degrees cancel, multiply both sides of the equation by
Pi.
So we have now 210 pi over what? Over?
180.
Very good, and that's equal to x. 30 times 6 is 180, 30 times 7 is 210. What am I driving at? This
You'll
would
have
be
7 pi over 6.
very good. And if we're given a negative rotation, that's okay. Setup's the same. What would that setup be?
Would it be negative 15 degrees over 180 degrees?
Very good. And that's equal to what?
Equal to x over pi.
Degree measures cancel, multiply both sides of the equation by,
By pi.
and we have negative 15, what? Negative 15
Pi.
over what? Over
180.
180, and that's equal to
X.
x. This is the first reduction we get that isn't something that we're doing mentally. We're going to use the calculator. Ignore the pi, and just tell me what 15 divided by 180 would be as a reduced fraction.
(1/12).
So now I have negative pi over 12. Very good. Now let's reverse it. We'll go from radians to degrees. So we're looking for now degrees. That will be our x. And the very first rotation we're given is pi over 3. I'll do this one. You'll do the next two. That seems innumerably fair to me. I know degrees over 180. So x over 180, 180 degrees, is equal to the radian measure we're given, which is pi over 3 divided by pi. And I just want to solve for x. Now it looks a little cumbersome, doesn't it? But it's not too bad. If I go ahead and rewrite x over 180 degrees, and if I invert and multiply, this becomes pi over 3 times 1 over pi. Now it's looking a lot better. Now it looks like I got x over 180 degrees is equal to 1/3. And if I multiply both sides of the equation by 180 degrees, I get 1/3 of 180 degrees, and that means x is equal to 60 degrees. Now, I do 1, you do 2, and we're going to kind of shorten the steps a little bit now that we see the process. Not a lot, but a little bit. I'll talk you through it, of course. Negative 3 pi over 4. What is the setup going to look like?
You will have x over 180 degrees.
Very good, and that's equal to what?
That is equal to negative 3 pi over 4
Okay,
divided by pi.
very good. So now I'm going to do two things at once. I'm going to multiply by,
180
and I'm going to invert.
and multiply.
Very good. So I have negative 3 pi over 4.
Right?
Then if I invert the pi over 1, it becomes what? It becomes
Times 1 over pi
good, and then I'll multiply by
by 180.
a little less to write that way. What cancels?
The pi's cancel.
Very good. So now I have negative 3 times 180 divided by 4. So instead of, what would that be? So I have negative 3 times 180 divided by 4.
That is equal to negative 540 divided by 4.
Okay, which would be
Negative 135.
beautiful. And one way I could have found that is by saying 4 goes into 180 45 times, triple it, 135 negative. One more and then we're done. One more and then we're done. We're going to take our setup, which would be
X over 180 degrees.
good. And what measure were we given? We're given what? We're given,
23 pi over 6
and we'll divide it by whom?
by pi.
Which I'll write as pi over 1. 2 steps at once. One step is to,
Multiply by 180.
so now I have 23 pi over 6. I'm going to multiply by 180. And I'm also going to do what?
Invert and multiply.
Very good. What cancels?
The pi's will cancel.
Sounds good. And then x is equal to, how many times does 6 go into 180?
30.
What's 23 times 30?
690.
And we're done. Thank you. We want to convert each radian measure to degrees. So that means we want to go from radians to degrees. And the way we're going to do this, we're going to set up a proportion. So the proportion works where you have an angle whose measures in degrees over 180 is equal to an angle whose measures in radians over the corresponding radian measure, which would be pi. So for part A, if I know that I'm going to have a radian measure of pi over 6, I'll write theta over 180 is equal to pi over 6 over pi. Now I just want to solve for theta, and the first thing I'm going to do is simplify this fraction that I have here. I know that pi over 6 over pi may be rewritten as pi over 6 over pi over 1, and then if you just simply invert and multiply, notice what you can do. You can end up canceling the pi's. So now I have theta over 180 is equal to 1 over 6. So if I multiply both sides of my equality by 180, I have theta is equal to 1/6 of 180. And it looks like theta is equal to what? Theta is equal to 30 degrees. For part B, I have a radian measure of 3. So again, I'll go ahead and say I'm going to just set up my proportion. Theta over 180 is equal to what? Is equal to 3 over pi. And now I'm just going to multiply both sides of my equation by 180. So I have theta is equal to 3 over pi times 180, which I'll write over 1. So it looks like theta is equal to roughly 540 over pi. And if I just want to write this in terms of the nearest degree, it would be roughly 172 degrees. We're going to convert 15 degrees to radians, which means we're going from degrees to radians. So we're going to use the proportion that says if I have an angle whose measures in degrees, that is to 180, as an angle whose measures in radians is to the corresponding measure of pi. So setting up my proportion, I know that I have 15 degrees that I'm starting with, so that is to 180, as some angle whose measures in radians is to pi. I'm going to multiply both sides of the equation by pi. So what does that mean? That means I have 15 over 180 times pi is equal to my angle whose measures in radians. Turns out 15 goes into 180 12 times. So my angle whose measures in radians is pi over 12. Find coterminal angles and reference angles of given angles. Coterminal angles are two angles that share the same terminal side, same. And a reference angle is something we're going to use a lot in this class. It's the smallest acute angle, which means what? Which means it's between 0 and 90 degrees, or 0 and pi over 2. That's formed from the terminal side and the x-axis itself. And it's always considered positive. So if I'm in quadrant 1, and I take a look at my reference angle, it would be the actual rotation if that angle was less than 90 degrees, or pi over 2. If I'm in quadrant 2, the reference angle is the shortest rotation from that horizontal x-axis. It would be this measure right here. If I'm in quadrant 3, again, it's that shortest rotation from the x-axis to that angle itself. And again, it's always the positive measure. And if I'm in quadrant 4, what I have is the shortest rotation from that horizontal axis to the terminal side. So I kind of have a visual. And students remember the visual as nothing more than a butterfly. Kind of like that, or a bow tie. So we want to find the reference angle, and we want to start in degree mode. So if I look at 60 degrees, first thing I'll do is I'll sketch 60 degrees. And I'll say, what's the rotation from the x-axis to that angle? And that would be 60 degrees. So to show the reference angle, I put a tick mark on the variable. 60 degrees. Now, I do 1, you do 3. 190 degrees. Now, let's see, 190 degrees puts me in which quadrant? In the
third.
Beautiful. So there's the rotation of 190 degrees. What is the rotation from the horizontal axis to that terminal side?
10.
10 degrees, because you're going from 180 degrees to 190 degrees. So my reference angle, T with a little tick mark, is 10 degrees. I do 1, you do 3. You got 1 out of the way. Negative 225 degrees. Oh goodness. I go in the negative direction, negative 180 and another 45. There's negative 225. My reference angle would be right here. It's the rotation, always positive, from the x-axis up to that terminal side. I'm not trying to give you a hint, but if my x-axis rotation was negative 180 and I had to rotate out to negative 225, because that's how I verbalized it, what's my reference angle going to be? It's going to be?
Would it be 45 degrees?
Absolutely perfect. And for the last one, 750 degrees, what color do we want? How about blue?
Yeah.
All right. So if I go ahead and take a look at my rotation for 750 degrees, all the way around would be what? It would be
60.
Another rotation would be?
720.
How much further would I have to then rotate?
30 degrees.
So there's my rotation of 750. From the way I phrased it, I think you know the answer. What's my reference angle going to be?
30 degrees.
The rotation from the x-axis up to that angle. Now that's for degree measure. Seems like we should be able to do the same for radian measure, huh? Let's do that. Pi over 3 is in which quadrant?
In the first quadrant?
Very good. What's the rotation from the x-axis out to that angle?
Pi over 3.
There is my radian measure of pi over 3 showing up as the reference angle. Go to 8 pi over 7 and say to yourself, oh goodness, my rotation would be into which quadrant?
The third.
Third quadrant. Very good. 8 pi over 7. I know that because pi would be, in terms of 7 pi over 7. To get the reference angle, how much further did I rotate?
1/7 of pi.
Beautiful. From 8 pi over 7 back to 7 pi over 7, that difference is pi over 7. How about negative 3 pi over 4? What quadrant am I in? I'm in which quadrant? I'm in the?
You are in the third.
Third quadrant. Because in terms of fourths, negative pi over 2 is negative 2 pi over 4. So I know it's negative 3 pi over 4 because if I wanted to rotate to negative pi, well gosh, that would be what? That would be negative, in terms of fourths, negative 4 pi over pi. When you look at the reference angle, it's this rotation right here. What would be the rotation from negative 3 pi over 4 to negative 4 pi over 4?
Would that be pi over 4?
Beautiful, and you kept it positive for me. Thank you.
Yes, I did.
The very last one is more irritating than anything else. Clearly, I have no problem being irritating, I suppose. If I go ahead and take a look at once around, see if I can pick, how about blue, right?
Sure.
Yeah.
Once around would be 2 pi, but that's 12 pi over 6, right?
Yes.
How much further would I have to rotate then to get to 19 pi over 6?
7 pi over 6?
That would put me in which quadrant? In the
The third quadrant?
third quadrant. In terms of sixths, pi would be 6 pi over 6. How much further would I have to rotate to get to 7 pi over 6?
Pi over 6?
Beautiful, and there's my reference angle. Thank you. Let's find a positive angle theta that is coterminal with an angle measuring 800 degrees, where theta is bound between 0 and 360 degrees, inclusive of 0 degrees. So the first thing I'm going to do is sketch my angle whose measure is 800 degrees. So I'm going to set up my axes, and I'm going to start the rotation along the positive x-axis. Going counterclockwise, if I go once around, that's 360 degrees, twice around, that's 720 degrees. That leaves another 80 degrees of a rotation. So again, once around was 360 degrees, twice around was 720 degrees, and what that meant is I then needed to rotate another 80 degrees to complete the 800 degree rotation. So my least positive angle that is coterminal with an angle measuring 800 degrees, well, that would be an angle with the measure of 80 degrees. We need to sketch the angle with the measure shown, and the angle is negative 45 degrees. Then we need to find a coterminal angle x, where x is defined to be from 0 to 360 degrees, inclusive of 0, but not 360 degrees. So first I'll go ahead and sketch negative 45 degrees. Negative 45 degrees means I'm going to rotate, because of the negative symbol, in the clockwise direction. If I rotate it all the way down to the negative portion of the y-axis, well, that would be negative 90 degrees. So I'm going to bisect that quadrant. Here's the rotation out to negative 45 degrees. So that's part A. Part B is I have to find that coterminal angle that has to be positive. So that means because that angle is between 0 degrees and 360 degrees, it's a positive measure of rotation, I'm going to rotate counterclockwise out to it. Well, I can do that, and I'll do that so that it's coterminal, meaning its terminal side matches up with the terminal side of the rotation that I just sketched. So what angle have we actually swept out? Well, had I rotated a full revolution, it would have been 360 degrees. So the measure of that angle, that would be 360 degrees minus 45 degrees. And what would that be? 315 degrees. That's the measure of the coterminal angle x. Thank you. Let's find an angle beta that is coterminal with the angle shown below, which is 19 pi over 4, where beta is equal to some angle that's between 0 and 2 pi inclusive of 0. So to make sure we're seeing the directions clearly, I'm going to sketch the angle 19 pi over 4. And I'll do that right here. Coterminal means the two angles, beta and this angle I'm sketching, will share a side. That's what coterminal means. And I just have to make sure that angle is less than 1 revolution around. So let's begin by sketching the angle 19 pi over 4. We rotate in the positive direction, a full rotation once around, that's 2 pi, with a denominator of 4, that's the same as 8 pi over 4. I have to keep my rotation going. I'm going to rotate a second time all the way around. Second time all the way around brings me to 4 pi, but with a denominator of 4, that's 16 pi over 4. I want 19 pi over 4, so I have to keep rotating another 3 pi over 4, which brings me to here. Here is my rotation of 19 pi over 4. Now coterminal means the two angles share the same side. But my angle beta must be a rotation from 0, and it could be 0, to 2 pi, but not all the way to 2 pi. So I want to rotate in a positive direction less than 1 complete revolution. So I would rotate, starting at the positive x-axis in the positive direction, to that terminal side. That's all we're doing. What is that rotation? Well, that rotation would be whatever 19 pi over 4 was, minus that rotation out to the positive x-axis when we rotated 2 full revolutions. So minus 4 pi, or 16 pi over 4. That rotation is 3 pi over 4. So my angle beta is 3 pi over 4. Find arc lengths, central angles, and radii corresponding to circular arcs. What you see before you is a circle, and you have 3 components. You have the center, and emanating from the center, you have a radius. Then you have another radius, and what are called subtend, they form the beginning and end of this arc along the circle. This angle that we see is called the central angle, and we have a relationship between the length of the arc, which is this piece right here that I'm highlighting, and r and theta, and that's that s is equal to r theta. And the only catch is that theta has to be measured in radians. So if I go ahead and think about this for a second, I can find each of these 3 components with that equation. If I know that s is equal to r theta, and if I'm looking for arc length, then I'm looking for s. As far as the radius is concerned, it looks like my radius is what? My radius is 10. Okay. And my central angle is, I want to say 60 degrees, but again in radians, it has to be in radians. 60 degrees, 60 over 180, that's 1/3 of it. 180 is the pi. 60 degrees is what radian measure?
Pi over 3?
Pi over 3, very good. So when I write s is equal to r theta, all I'm going to do is substitute in some stuff. I'm going to substitute in for r what? I'm going to substitute in for r
10.
and for theta I'm going to substitute in a
Pi over 3.
and I'm basically done. So it looks like s is equal to,
S is equal to 10 pi over 3.
beautifully said. And that's the length of the intercepted arc. If I can find arc length, I should also be able to find the measure of a central angle just as easily. Now in the second example, what we want to do is we want to find the radian measure of a central angle on a circle of radius 8. So I'm just going to mark that now that we see what we're doing. That intercepts an arc of length what? Of length
7.
So it looks like s is 7 and r is 8.
Yep.
And we know s is equal to r theta. So I'm just going to make a substitution. You're going to make a substitution. In place of s, we'll put a
7.
In place of r, we'll put a
8.
8. So now what does our equation read? It reads what? It reads,
7 equals 8 theta.
and to solve for theta, we do what? We
To solve for theta, we divide by 8 on either side.
Now this answer may look weird, but it sure looks like theta is equal to what? Is equal to
7/8.
7/8. And theta is always what unit of measure?
Radian.
Radian.
Radians. And 7/8 is a number, so that's actually just fine. So if you actually think about what we've done here, and I don't want to spend a whole lot of time, but I do want to think about it for but a moment. If theta is 7/8, that's a little bit less than 1, right?
Yes.
So when I take a look at my radius is 8. Okay, so that's here. This distance is a little less than 1 radian. And so that distance along the arc is 7. Here's the 1, here's the 7. Well, what do we still have to find? We still have to find the
radius.
We haven't done that yet. We're going to find the length of the radius of a circle if the arc length is what? If the arc length is
3.
All right, so s is 3, and we're given the central angle, theta is what?
Pi over 6.
Now we know the formula. The formula is?
The formula is s times r theta.
S equals
S equals?
r theta.
Very good. What's the substitution look like? In place of s, we'll put a?
A 3.
Okay, in place of theta, we'll put a...
Pi over 6.
Very good. So what would my equation look like now?
It would be 3 equals r times pi over 6.
How do I solve for r then?
Would you divide by pi over 6?
That's
on both
great.
sides?
And that's the same as inverting and what? Inverting in?
And multiplying.
And multiplying. So when I do that, it looks a little strange, doesn't it? But that's okay. R is equal to, now just multiply straight across. R is equal to?
18 over pi.
18 over pi. Excellent job. Thank you. Assume the orbit of Mercury around the Sun is a perfect circle. Let me sketch that perfect circle for you. Here's the Sun, and here's Mercury. Mercury is approximately 36 million miles from the Sun. So my radius of this circle is 36 million miles. In one Earth day, Mercury completes 0.0114 of its total revolution. So this portion of that rotation is what Mercury completes in one Earth day. The question is, how many miles does it travel in one day? So we're trying to find the length of this arc length, S. So what I'll do is I'll find the circumference of this circle, which is the distance all the way around. The circumference is 2 pi r. And once I find that circumference, I'll multiply it by 0.114 to find the actual distance that S would be. So the circumference is equal to 2 pi times the radius, which is 36 million miles. Well, if I multiply that out, that's 72 million pi, which is approximately 226 million. Now that distance is Mercury's orbit. We're looking for this distance of the arc length it has traveled. And that distance would be 0.0114 of that amount, of 226 million miles. And that would be approximately 2,580,000 miles. So that's the answer to part A. For part B, I'd like the radian measure that angle was swept out to allow Mercury to travel 2,580,000 miles. So that angle, that measure, would be this angle right here. Now I have a calculation that will do that. I know my arc length is equal to r theta. So that's what I'll use for part B. To find the radian measure, I'll substitute in for S, the arc length, that distance Mercury traveled, which is 2.58 million. And that's equal to R, and that radius was what? It was 36 million. Times theta. And I'll just solve for theta. I'll divide both sides of my equation by what? By 36 million. So if I divide both sides of my equation by 36 million, I find my radian measure to be approximately 0.0717. An automatic lawn sprinkler located right here sprays a distance of 20 feet while rotating 30 degrees, as shown in this figure below. And I want to know the area of the sector, which is this area that's shaded, and that's the sector of grass the sprinkler actually waters. Well, the area of a sector has a formula, and that formula is 1/2 times theta times r squared. Now r is the radius, and I know what the radius is. The radius here would be what? It would be 20, because if I drew my whole circle, I can kind of see that's circle appear, and I can see that 20 is that radius emanating from the center, which is the lawn sprinkler. Now the central angle is what theta is. And the only thing you have to be very careful about here is that this angle theta has to be in radians. Now I know it's the measure of the central angle, which is 30 degrees, but 30 degrees, if I went ahead and wrote that measure in terms of radians, is pi over 6. So that's the substitution I'll make. So making that substitution, I have the area is equal to 1/2 times the measure, that's central angle, which is pi over 6, times 20 squared, r squared. And I want to keep the answer exact, so I'm going to take a second to just rewrite this line as 1/2 times pi over 6. I don't want to change the value of pi to 3.14. I would like the answer exact. And then I'm going to multiply by 20 times 20. And you may wonder what I'm doing, but I'm just trying to see if I can look at that answer in terms of a reduced fraction times pi. 2 goes into 20. How many times? 10. So now I have my area is equal to 10 times 20, which is 200, pi over 6. I can still simplify a little more. I can divide a 2 into the 6 and the 200 both. So my area now becomes 100 pi over 3. Now if I did want to go ahead and approximate it to the nearest square foot, that would be 104.72 square feet, rounded to 2 decimal places. Thank you.